Right, so in the previous videos, we worked on air-cooled heat sinks that used or worked with the natural convection method to remove heat from CPUs with or without hotspots. And we figured out that air-cooled heat sinks aren't good for or efficient for chips with hotspots. So we want to do a water-cooled heatsink with hotspot, and we're going to do an example here, and then we're going to modify it in a future video to see how we can take advantage of a water-cooled heatsink to efficiently remove heat from chips with localized high temperatures or hotspots. This is an overall 3D view of the model I'm going to be creating. Actually, in the simulation, I'm going to take advantage of symmetry so that we spend less time on the simulation. But I just want to show you the full picture. This is not everything you can see because there's stuff inside the heatsink that are covered. So I'm going to show it right here. That's what it looks like, what we're going to model. So the gray side is the body of the heatsink. We have channels in the middle. The blue is where the water is going to come in and then is going to go out after removing heat from a chip, which is 25 millimeters by 25 millimeters. So the 25 by 25 in here is going to cover the chip. In the middle, we're going to have a hot spot. The thickness of the wall is 2 millimeters. We have a cylindrical inlet and a cylindrical outlet. They're identical. The dimensions are given. I'm going to come back to this drawing as I make the model in COMSOL because I don't expect to remember. But if you want, you can pause here and take a screenshot so you can refer back to this picture or have it next to the video as I'm going through modeling this thing. And another picture I want to show is the side view where we have the thickness of the entire heatsink is 10 millimeters. And the entire interior part is 6 millimeters, like a cavity or opening where water can flow through. The cylinder itself is 5 millimeters in diameter and 3 millimeters coming out of the heatsink. And this is another view of it, so we can see what it is. There's a 1 millimeter thick wall for the for the inlet and outlet. And this is the hotspot. And the bottom surface of the heatsink, the entire chip is a 25 by 25 square, and a square 10 by 10 millimeters squared is the hotspot. The power to the hotspot is 60 watts, and the power to the background, which is the gray side, is 100 watts. So, like I said, I'm going to take advantage of symmetry when I'm simulating this thing or analyzing it, which means I'm going to model half of it. But as I go step by step in designing this geometry, I'm going to do an eighth of the model, and then I'm going to do mirrors to make a half model after that. So I'm going to create this quarter that I'm showing right here, and then I'm going to mirror in the X direction or Y, and then mirror vertical to the plane. So with that, let's go to COMSOL, right? So in the new, I'm going to go into first select space dimension. It's going to be a 3D model. Then I'm going to have to select physics. Now, in comparison to an air-cooled model, this is a water-cooled model, which means I'm going to have multiphysics analysis of heat transfer in solids and fluid flow. And that is done as a conjugate heat transfer analysis. If I click in here, I have a laminar flow, which means the velocity of water inside the heatsink is small enough that the flow stays laminar. And I can also do turbulent flow. For the sake of this problem, I'm going to stay with laminar. And if you look at the information here, it tells you that it's a laminar flow and is good for some analysis and non-isothermal flows, and every information that I need about this are given here. If I click on this heat transfer, it tells me that it's going to calculate temperatures for the solid, and then as far as the fluid goes, it's going to calculate the velocity and the pressure, and then also get the multiphysics to couple these two physics. Going into the study, I'm only interested in the steady state, so I'm going to double click on stationary, and then I'll be taken to the main window. And the first thing I want to do here is to change the length unit from meters to millimeters. That's the first thing I want to do. And then I want to start making my model. Going back here again, like I said, I'm going to have a weird geometry that's not conventional, like a cube or a cylinder here. So I'm going to do a 2D polygon, and then I'm going to have to extrude it afterwards. So I have done the calculations to find the coordinates of the points here, 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 and here. So I'm going to have to create 5 points. I'm going to have to give the x and y coordinates of each of these points. Again, I have done my calculations before, so I'm going to just input them in here. So in geometry, because I'm going to do a 2D, I'm going to have to click on a work plane to get into the 2D, and it's asking me what kind of plane I want to make. It's good in the XY direction, so I'm not going to change anything. If I click on plane geometry, I'm taken to what I have to do in making my model. So let's create a polygon, and I have to give the dimensions for that. So let's say the first point is 0 and 0, and it would show me where the point is, right? I can go to the next point in the X direction or the Y direction, depending on which way I want to create. So this is 25 total, but I'm creating half of it. So it's going to be 25 divided by 2, or 12.5. And X is still going to be 0. So 0 in the X direction and 12.5 in the Y direction. If you're not sure about the divisions, if dimensions are not straightforward, you can just say 25 divided by 2 if that's how you want to do. Still, COMSOL will recognize it. If I zoom out enough, you see that is created over here. If I build selected, I only have a line. I can give the other 5 points. The next one is going to be, so after here, I have a line at 10 magnitude and 60 degrees. And the X direction is going to be 0 plus 10 times cos of pi over 3, which is 60 degrees. In the Y direction, I have to add 12.5, the previous point, plus 10 times sine of pi over 3. So if I build this, now this is what I've got. I need to have 2 more points. The next point is going to be 12.5 and this same y, so 12.5 in the X direction, and the same y here. So this is what I would get. And finally, I have to move down to x equals 12.5 and y is equal to 0. So this is the last point. So I get the first, or the base of the heatsink modeled. Now I have to create the interior, like 2 mm thickness walls and the fins or the channels in the middle. For that one, I'm going to create another work plane. So let's build this one first and still look at the XY plane and create another work plane similar to the previous one. But now I'm going to create another one. Again, I have done the calculations for all the points here, 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 and here, and also the dimensions of the channel. So this time, again, I create a polygon. The X is going to be starting from 2 to give the 2 mm thickness of the wall, and the Y is going to be 0. That's the first point right there. And then I move to the second one is going to be 2 and 12.5. We'll move out and let's build selected. You see this is the 2 mm wall. Then the coordinates of the third point right here is going to be, again, based on my calculations, 10 times cos pi over 3 plus 1, and this is going to be 10.5 plus 10 times sine of pi over 3. If I built this one, this is what I get. Now I have to come down, or I have to move forward in the X direction with the same Y, so I'm going to copy this. So 12.5 and this is what I get. And finally, in the X direction, I'm going to be at 12.5. In the Y direction, I'm going to be at 0. So if I build this, so I get the interior. Now the next thing I have to do is to create these channels. So the channels are 1 mm thick and 25 mm long, but again, I'm doing half of it, so I'm going to be creating a 12.5 mm long rectangle. The thickness is 1, so I'm not going to change that. And the height is 12.5. And the corner is going to be from here 0, 2, and 1 is the channel width. So 3 in the X direction. So if I build this, the first channel is created. Now I want to have, if I look at my geometry, I have 10 of these, but for the half model, I'm going to have 5 of these channels. So I have to copy this 5 times in the X direction with the spacing of 1, the channel width, plus 1, the wall width. So to do that, I find array from transform. First, select what I want to array. And then in the X direction, I'm going to have 5 of them. And the distance is going to be 2 between each of the adjacent walls. And I can say build all, and that is what I need. So if I come back here and say build all or build selected, I see the interior also is created. The next step is to extrude these 2 work planes according to the requirements. So the interior is 6 millimeters. Again, I'm doing half model, so I have to do 3 millimeters in the Z direction. And then actually the interior was 6 millimeters. The exterior is 10 millimeters. So that would be 10 divided by 2, 5. So I select extrude, pick work plane 2 first, and say extrude by 3 millimeters. And say build selected. You see a 3D model of that one. Another extrude for the exterior. Now I have to select work plane 1, but it doesn't select automatically, so I click it. And then I say it's 5 millimeters thick. So now this is done. I don't have to worry about doing the overlaps and anything else, because once I'm done and I say build all, COMSOL will take care of the overlaps, and that's convenient, so I don't need to worry about that. The next thing I have to do, going back to my model, is this cylinder. So it's 5 millimeters in diameter, 3 millimeters height, but if I go back to this picture, you see that it has to come down or come inside so that I can merge the fluid domain. So I'm going to have to say 3 plus 2, the thickness of this wall, 5 millimeters high. And then the center of this cylinder is going to be right here. And again, the thickness of the walls of this inlet outlet is going to be 1 millimeter. So to do that, I have to create a cylinder. It takes the radius, so it's going to be 5 divided by 2, it's 2.5, and the height is going to be 5. So if I just do this, I'm going to have this cylinder. Not only it's not in the right place, it's also in the wrong direction. That's because the axis is in the Z axis, so I'll change it to Y. If I do this, now the direction is correct, but the location is not right. In the X direction is going to be 12.5. So let's do that first. So it moves right. The Y direction, it is has to be right here. So if I go back to my second work plane in the polygon, pick one of these and come into my cylinder and put in the Y direction, Control V or paste, it will be in the right place. Now, still we're missing something, and that's the thickness of the wall. And the easiest way to do this in COMSOL is to take advantage of the layers. And layers will basically create a layer around this. It can do in the bottom and the top as well, but I don't want to do in the top and bottom. I just want to do on the sides a 1 millimeter thick layer. So I click that, and that is perfectly done. Now, again, in order to take advantage of symmetry, I need to make my cylinder a little bit different. I have to only have a quarter of the cylinder, which is not an option that I could take advantage in COMSOL, so that I have to do individually. So the first thing to do is to select domains instead of objects. So I can come and select these 3 domains and just press delete on the keyboard. So those 3 are gone. The next thing I want to do is to cut this cylinder into 4 segments. Let's look at it in maybe in the other direction like this. To cut this into different segments, I take advantage of partitioning domains. So I create partition domains. And the first thing I want to do is to partition this domain with the work plane 2, which is convenient. That's conveniently selected. And once done, if I build selected, now I see that my domain is divided into 2 domains. So I can select this one and press delete. I have to do the same thing again, but in the Y direction. There's no work plane defined there. But to do that, I can say partition domain. I want to partition this domain, this time with an extended face. And let's extend this face. And then that basically goes through the half of it. So if I press build selected, now I have this domain divided into 2 halves. So I can say delete this, and that's basically what I needed. Just hope that this maybe, okay, I guess I did run something in here. What I wanted to do instead of, right, so I'm doing domain. All right, that was a mistake there in the partition, in the delete. Okay, so can delete that, build selected. Okay, that's properly done. Okay, and previously I had forgotten to change this into domain selection, so it only deleted the boundary. So this is 1/8 of my model. Now what I have to do is to mirror this in the Y direction to make 1/4 of it. To do that, I go here in transform, say mirror, and before I forget, keep input objects. And like I said, the first step is to mirror in the Y direction. So I change Y to 1 and Z to 0 and say build selected. Oh, I haven't selected anything yet. Oh, that's empty. Okay, what I have to do is to select everything, and to be sure that I select everything is do a select box, go here and say select everything. Now I have the thing done. Right, now I have to mirror this in the Z direction as well, because in the bottom surface of this heatsink I'm going to have heat flux, and then on the top surface I'm not going to have anything. So to do that, I do another mirror. Again, select all and a box here, and this time in the Z direction is fine, so I just say build selected, and I forgot to do this. Okay, so that is done. So I can basically have half a model. One thing I also want to do, if I look at it from the XY direction, see that this end is at 0, 0. But what I want to do is to, actually no, this here is at 0, 0 in the XY coordinate. But I want this whole thing, this middle surface, to be at x equals 0. And this is my preference. It's not necessarily that everybody does that, but I just want to do it. And in order to do that, I do move. Again, I want to select everything. And then say in the X direction, move minus 12.5 millimeters. So I do that. Now this surface is at x equals 0. Again, that's my preference. It's not a necessary thing to do. Now, if I look at this, I want to go to the bottom surface right here, and I want to define my chip with the hotspot on it. It's a 2D thing, so to do that, what I can do is create a work plane first. And to do that, I stay with the XY plane, but I say go down in the Z direction by 5 millimeters. That's the half of the thickness of this heatsink. Build selected. That's where the bottom surface of this heatsink is going to be. And right there, I'm going to create 2 things. The first thing is a rectangle width 12.5 in the X direction and height 5 or 25. And the corner of it is going to be at, I think, minus 12.5 and minus 12.5. So I built this one. That's right. Then the hotspot in the middle is going to be 10 by 10. But again, since this is a half model, so the X direction is going to be 5 millimeters. So rectangle, 5 in the X and 10 in the Y. And the corner is going to be at minus 5, minus 5, right there. And I can move out of here. And let me clear this and build selected. Now the chip and the hotspot are selected. And I can say build all. And at this point, COMSOL goes through any objects or domains that have overlapping and takes care of that. So one thing that's very important to do to make life easier is to define or create some definitions, right? So what I want to do is first I want to create an explicit definition for the water or the liquids, right? So in order to do that, first thing I want to do is to hide some of the stuff that are hiding the fluid from my view, right? So I want to hide these things so I can see what the fluid, where the fluid is. And then I can select domains. I can select boundaries if I needed to, but in this case it's domain. So all of these that I'm selecting are gonna be used for the fluid. And let's give it a name like water or fluid if I wanted to. I'm gonna call it water. Doesn't matter, it's just a name. Then I want to create another explicit definition, and for that I want to remove my water so I don't accidentally select the water domain. Right, these are all water that I'm hiding, and basically to hide anything, just click on this eye with a line on it to remove the eyes or remove domains. Now I want to select another explicit. I'm going to call it heat sink, and let's first do a box select because everything else is hidden. And then I still have the top half to select, so reset hiding, yes, and select, I need to zoom in here, 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 and here. Oops, here. So that is selected. If I do a wireframe, you can see that this is where the heatsink body is. That's the solid. And then if I select fluid or the water, this is where the water is, right? The other thing I want to select is the inlet and the outlet. So let's remove the wire thing. Now this time I want to create another explicit. I'm going to call this one inlet and select these two, or actually I need to change it from domain to boundary, this and this boundary. And then for the outlet I'm going to select these two surfaces. So another explicit, let's call it outlet. And I'm going to select this and this. Then in the bottom surface of the heatsink, I'm going to define the background and the hotspot. So, oh, I selected, sorry, that would be a mistake. Let's see, this is the inlet over here. The outlet should be on the other side. I forgot to change this from domain to boundary. Okay. Right. Then let's select or create definitions for the background and the hotspot. So another explicit, I'm going to call it hotspot, and select these. Okay, again, I made a mistake. This is boundary. It's easy to forget that. And then another explicit boundary is going to be the background. And this is the background. And let me save this first before I move forward. Let's call this water-cooled heatsink with hotspot and save it. I did not do any parameters here because I'm not going to change the geometry, but what I want to define two parameters here, one for the inlet temperature and one for the inlet velocity. So Tn for inlet temperature is going to be, say, 293.15 kelvins, and I'm going to call this inlet temperature. And the next thing I want to create is Vn, say 0.1 meters per second, and that's the inlet velocity. And save this. So far I have everything that I need in order to make the model. Now the next step is going to be defining the materials and appropriate solid and the fluid selections. This one I'm going to continue in the next video. So this is part one of creating a water-cooled heatsink for CPUs with hotspots. I'm going to save here, and I'm going to see you in the next video.